In this video, we're going to look at the intersecting chord theorem. We're going to work through 3 different examples and look at how we can find missing lengths in the circle. So that missing length might be the radius, it might be a chord, a tangent or a secant. Whilst the proof of these is certainly beyond the scope of the course, we will look at roughly how each one works as we go through them. So let's start with the first. And there's a circle. So what we're going to do on here is put a chord. A chord cuts across the circle. So from circumference to circumference we have this straight line. Another chord might go across there. We can have these chords anywhere. These chords now could be from here to here, it could be from there to there. If we put this one over here, that could be like so. The intersecting chord theorem says if we have 4 points, A, B, C and D, and they meet now at this point in the middle, which I'm going to call X, we can say that AX multiplied now by BX will be equal to CX multiplied by DX. You won't be expected to show the proof of this in an exam, but we'll have a look of why or how it works from here. So if we grab up a circle, from circle theorem we know that angles in the same segment are equal, or if you like, the bow theorem. So if I now drew a bow, we know that these 2 angles are the same, and we could call those X. So we'd have now X just here, and we'd have X just here. The angles at the bottom will be the same, and we can say if this one is Y, then this one is going to be Y. These are opposite angles, so these 2 will be equal, and we will call those Z. What we have here are similar triangles. So this triangle is similar to this one. So if I put on here that this was going to be A, we've got now big X in the middle, we had B just here, we've got C just here and D just here. I'm essentially replicating what I've got here. Slightly different configuration, but exactly the same. So if we look at these as 2 similar triangles, from this we can say now that AX over CX will be equal now to, and we would say DX over BX. So now DX over BX. Cross multiplying, we've got now AX multiplied by BX is equal to CX multiplied by DX. So that gives you some idea of why this works. Using what we've learned before in circle theorem, these are similar and we can simply say this. Now in all reality you're highly unlikely to be asked to show that. What you might be given is a circle, and you would be given now the 2, and we'd have a chord here and a chord just there. We might be told that the length from here, and again it might be that A is here, B is here, C is here, and then D is here. We'd have X now at the point of intersection. We might be told this is going to be 3, this is going to be 10, we might be told that this is going to be 5, and we would want to find out now the value, and let's just call that Y. So this is CX would be Y. So all we would need to say is 3 multiplied by 10 is going to be equal to 5 multiplied by Y. It's that straightforward. This one multiplied by this one is equal to this one multiplied by this one. So from there we can see that Y is going to be equal to 6, simply dividing both sides. So 30 over 5 is equal to Y. So if this was in centimetres, Y would be 6 centimetres. Now if you look at that, we can see quite clearly why that's the case. I've set here 5 and 10, so we can see now that this is going to be 3 and 6. Hopefully that's quite intuitive. If we had numbers that weren't as obvious, then you probably might, well, you may not be as confident in that. All I've said now is that one times by that one is that one times by that one, and we can see now that they are, in fact, if I just jot these down, let's go ahead and do that. So let's do that, and let's do that. We can see that these are similar triangles. I've simply scaled one up by now a scale factor of 2. So that is the intersecting chord theorem, and we're going to look at some basic examples of that later. Okay, let's go on to another one. Let's grab up another circle. Whilst this is in the intersecting chord theorem chapter, it's actually a slightly different theorem, and this is called the secant-secant or secant theorem. A secant is a line that cuts through the circle, so it's cutting at this point and cutting at this point. If I drew another one and they meet at some point out here, and we will label this up, if this is going to be A, this is going to be B, this is going to be C, and this is going to be D, they will meet at this point X, and we can say that AX, so the entire length of this line right here, multiplied now by BX, which is the line from the circle to the point, will be equal now to CX, which is the longer part, multiplied by the shorter part. Now often pupils, when they're doing this, forget to now add the parts up. So what we're saying is the following. We're saying now that this length multiplied by this length will be the same as this length now multiplied by this length. The proof again is beyond the scope of the course, although I might do one in another video. It's quite interesting to look at. So let's go ahead now and do an example of this. So let's do a basic example. Okay, so here's a circle. So let's put now the secant on. So here's a secant. Secant cuts through the circle, and then we'll have now another one just here. So say we had that this was going to be, let's say this was going to be 4, and let's say this was going to be 5. Let's say that this distance right here is going to be X, and that's this one from here to here, and let's say this is going to be, let's say that this is going to be 5. So if we have now big X here, what we can say is this entire length, the entire length is the 4 plus the 5. 9 multiplied by 5 will be equal now to this entire length, which is going to be 5 plus X multiplied now by X. So that's what we end up having. If we had it the other way around, we could make our work slightly easier, but essentially this is what we're going to have. So we go ahead and solve that as now a quadratic equation. So this is a slightly harder example, given that I've given this to be 5 and X. If we looked at another scenario, we could make it slightly easier, but as we go through, we'll go on and solve. So all you do is solve this as a quadratic equation. So that's called now the secant-secant theorem, or secant theorem. Okay, let's have a look at another one. Let's go for now the circle again. So let's grab up a circle. I'm going to have now a secant, and the secant line will do something like this. So at the moment, that's a chord. That becomes a secant. I'm now going to draw a tangent. A tangent, remember, touches the circle like so. I'm just going to leave the tangent at the point of intersection. So if we leave that there, we've got the following. So let's call this point now A. This is going to be A. We've got B, and we've got C, and we've got some point X. Now, this is called the tangent-secant theorem, and we can say the following. We can say that BX multiplied by CX will be equal to AX squared. So let's say we didn't know this length, and let's say that this was going to be Y. This was going to be 5, and this was going to be 6. We could say now that this length squared, Y squared, would be equal now to 11, those two added up, multiplied now by 6. So Y is going to be the positive square root of 66. And then whatever units you're using, that's what you'd have. That doesn't break down to a nicer number, so that's what we would do. So that is an example of now the secant tangent theorem. So if you've got a tangent, you square this length right here and set it equal now to BX multiplied by 6. So AX squared is equal to BX multiplied by 6. There is another one, and we'll look at an application of that as we go through the questions. So let's start off now looking at some questions. We might be given now something like so. So W, X, Y and Z are 4 points on a circle. P is the point of intersection of the chords WY and XZ. So that's just there. Now we need to work out the length of WY. So let's go ahead and just write now that this length right here, our unknown length, is going to be, let's just call this X. So what we can say then is this distance, X, multiplied now by 8 must be equal to 9 multiplied by 4. So from here, 8x will be equal now to 36. Dividing both sides by 8, that's going to give us now 4.5. So I can say that this distance right here is going to be 4.5. So we've got 4.5 plus 8. We want wy. So all we're going to do is add the 2. So we can say now wy is going to be equal to 8 plus the 4.5. And we end up now with 12.5 centimetres. So all we've done is simply use now the intersecting chord theorem. Nice and straightforward. We've got this scenario. We've got this point of intersection right here, and I've said now that this is the unknown. So the unknown is going to be here, x, then we've got 8, we've got 9, and we've got 4. This one now multiplied by this one is equal to this one multiplied by this one. Okay, let's look at another example. A, B, C, and D are 4 points on a circle. DA is 23 centimetres. DP is less than PA. So there's DP, so that's shorter than PA. We need to work out the length of AP. So if we look at the last one, we've got now these two lengths. So I'm given some of the length here. This time we don't have that. So let's say that this is going to be now x. I want to work out the length now of AP. So let's say AP is x. This must be now 23 minus x. This whole line now, DA or AD, is going to be 23. So we've got 23 minus x and x. So we can say x multiplied by 23 minus x will be equal to 12 multiplied by 5. So we got 23x minus x squared is equal to 60. I'm going to set the left-hand side of this equation to 0, and I've got a quadratic. So adding x squared to both sides, subtracting 23x, and then we've got the 60. Two numbers that multiply to give positive 60 add to give minus 23. That's going to be x minus 3, and then x minus 20. So we can see that x is going to either be equal to 3, or now we can say x will be equal to 20. We're told now that this length is shorter than this one right here. So that must mean that x is going to be on here 20. So this is the value of x. So we've got to take the bigger one. And then this one is going to be now 23 minus x. This will be the shorter one. So we've got now 3 and we've got 20. Now if you look at that right here, we can see again with similar triangles, the 3 and the 12, the 4 and the 20. We can see that's scaled up by 4 and that's scaled up by 4. These are similar triangles. So the length of AP is going to be 20 centimetres. So AP is equal now to 20. So all we've done is use a bit of algebra, solved a quadratic equation. Okay, A, B, C and D are 4 points on a circle. PAB and PCB are straight lines. In part A, we're asked to work out the length of PD, and then in part B, we need to write down the length of CD. So it's telling me I need to do some calculations at first, and as a result, I can just write down the answer. We're being told that these are straight lines such that I can use the secant theorem, or if you like, an application of the intersecting chord theorem. Okay, so what do we know? Let's take this whole length right here. This whole length is going to be as follows. We're going to have now 6 plus 10. That's going to be 16. Multiplied now by 10. So I'm taking the longer length right here. I'm saying now that B to P multiplied by A to P will be equal to DP times by CP. Okay, let's go ahead and do this. So let's set this equal now. Let's just call DP now x. Let's say that this whole length right here is going to be x. So what we're going to have then is x multiplied by CP, which is going to give me now 5. So we've got 160 over 5 will be equal to x. 160 over 5, that's 32. So 32 is going to be the length of DP. It's the entire length. It's from there to there. So if that's going to be 32, we need to write down the length of CD. That's simply going to be the 32 minus the 5. So this one is the 32 centimetres. This one, therefore, is going to be 27 centimetres. 27 and 5 make 32. So a nice straightforward example of how I've taken now all of this distance right here to be one value of x. So I've said now that d to p is going to be equal to x. Okay, let's look at another one. A, B, C and D are points on a circle. Show that x satisfies the equation x squared plus 30x is equal to 216, and we need to find the value of x. Okay, let's go ahead and do that then. So what have we got? We can say on this that BP multiplied by AP will be equal to DP multiplied by CP. So all I'm going to do is multiply them. So we've got now 6 plus 12, which is going to give me now 18, multiplied by 12 will be equal to this whole length. And we need to be careful here. This whole length is going to be 30 plus x. So 30 plus x multiplied now by CP, which is just going to be x. So let's go ahead and write this out. So on here, what we've got, 18 times by 12 is 216. Then we've got now expanding the brackets 30x plus now x squared. So we can write this as x squared plus 30x will be equal now to 216. And I'm just going to state this in my workings. I know this is the case. The whole length multiplied by the length outside the circle is equal to the whole length multiplied by the length outside the circle. That's the secant theorem. Okay, we need to find the value of x. So what we've got here is a quadratic equation. X squared plus 30x, and then we're going to minus 216 from both sides. Now, this looks like it's going to factor. I know that 6 to the power of 3 is equal to 216. Now, that's going to be 36 times by 6. So 6 cubed, I could do that. So if I look at this, the factors now, we're going to have x plus 36 and then x minus 6. So that does factor. So we can see that x is either equal to minus 36 or x is equal to 6. That cannot be the case. X can't be equal to minus 36 as minus 36 is not a length. This length can't be a negative. So we can say that x is going to be equal now to the 6. So if we take this value right here, x to be 6, we've got now that will be there 6 centimetres. So we've just simply found that, and I appreciate that it doesn't look accurate, but that's what we would find. So that's using the secant theorem. And those examples now, the 4 that we've looked at, are highly likely to be in most exams or similar kinds of questions. If we look at some others, let's have a look at something else. Okay, A, B and C are 3 points on the circle. Cent-O, radius 4.5. PCB is a straight line. PA is a tangent to the circle at A. That's fine. We need to work out the length of OP. So OP is going to be this right here. Now this relies on a bit of circle theorem. What we can say though is the following. Based on what we looked at, this now is the secant tangent theorem. We can say that AP squared is equal to BP, let's write BP, multiplied now by CP. So let's go ahead and do that. Let's say that this length is going to be x. So what we can say then is x squared will be equal to this whole length, and that length is going to now be 9. So we're going to have 9 multiplied by 4. So what we've got here, this whole length right here is 9, that length is 4, so we can see x squared is going to be 36. And this works out quite conveniently. X squared is 36, x is equal to plus or minus square root of 36, x is going to be 6. We've got to take the positive as now it's a length. So that is going to be 6. So x is going to be 6. What we now need to do is work out OP. And I'm simply going to draw now some lines on here. If we have a tangent, circle theorem tells me that that's going to be a right angle just here. So straight off, if I'm doing this in an exam, show the examiner that that is going to be a right angle. We've already got the radius. We're told the radius in the question. we've just found now x. So what we've got then is the following. We've got that this is going to be, the radius is 4.5, and then we've got 6 right here. So if we call this now, this length y, just using Pythagoras, we can say y squared is equal to now x squared plus 4.5 squared. So 4.5 squared plus now the 6 squared. So let's put that in a calculator. Let's go ahead and do that. We want the square root. So square root of 4.5 squared plus 6 squared. So that's what we've got, and that's going to give me 7.5. So y is going to be equal to 7.5 centimetres. So I can put on here then that O to P is 7.5 centimetres. And you might have spotted that if you just look at this one right here, 4.5 squared is going to give us 20.25 plus now 36, which gives us 40. What's that going to give us? 56. Let's scribble that. 56.25. Now, a little trick here. If you're multiplying 0.5, so something 0.5, 7.5, 6.5, let's find this. So 56.5. So it's the square root of 56.5. Now, 4.5 squared is the same as doing 4 times by 5, then just adding 0.25. So that gives me 20.25. If we look now at 7.5, it's 7 multiplied by 8 plus 0.25. So if you ever want a little trick, there's a little trick. You take the number either side, multiply the two, and add 0.25. So that's an example now of using the secant tangent. You don't have to refer to these, you don't have to prove them. The proof is quite nice, but essentially you just have to remember that one squared is equal to this one multiplied by this one. So there we go, we've answered that question. Okay, O is the centre of the circle. YOW is a diameter, so YOW, that's fine, YOW is a diameter. M is the midpoint of XZ. Now again, if we've got a chord and we've got a perpendicular bisector, which this is, we're being told that M is the midpoint. Remember, perpendicular bisector cuts it in half. This will find the centre of the circle. Later on in your studies, you'll see that if you've got two chords, you can locate the centre given the two chords. What we need to do is the following. So the radius of a circle is C, that's fine. So this distance right here is C. O to M is going to be A, M to Z is going to be B. We need to show that C squared is equal to A squared plus B squared. Okay, let's go ahead and do that then. So what we've got then is the radius of a circle is going to be C. We're being told now that O to M is A, so that's A. Now if we consider that this is also, O to W is also a radius, so this is going to be C minus A. So if I just put that on, so C is the radius, we're told O to M is A, therefore W to M or M to W is C minus A. C minus A plus A gives us C. We're told now that M is the midpoint, so this is going to be B and this is going to be B. All I'm going to do is use intersecting chords again. So what we can do, if I just draw this up now, we've got this scenario. So we've got either side. We've got B just here, we've got B just here, we've got C minus A, and then the other side we've got C plus A. So we know that these two multiplied are equal to these multiplied. So we've got C plus A multiplied by C minus A is equal to B multiplied by B, or B squared. This is a difference of squares. This gives us now C squared minus A squared, and that's going to be equal to B squared. So just adding now the A squared to both sides, C squared is equal to A squared plus B squared, as required. If you want to expand this out, you'll see that those CA terms drop out. So we've got C squared minus CA plus CA minus A squared, and that is the difference of squares. So when we expand, for example, x plus 1 and x minus 1, we see that that's x squared minus 1. It's the difference of squares. So we've shown that now, and I would want to tell the examiner now that I'm doing the following. I'm doing on here now ym, let's do ym multiplied now by mw will be equal now to, we're going to have x to m multiplied by z to m. So x to m multiplied by z to m. And then I can just go ahead and show that. And that's just the intersecting chord theorem. Now, just branching off of this, you might in an exam get a question that looks something like this. So let's just take this now. The question that you might be given in the exam is to find the radius of a circle. And I'll briefly look at this. We might be given the following information. We might have this little snapshot here, and we might have this. What we would be asked to do is now find the centre or the radius of a circle. Okay, let's just see what, and when I say you'd be given this information, what you would see in the exam is just what's in the red box. And you might be told now the following. You might be told that this distance right here, the whole distance across, is going to be 10, and you might be told that this is 3, and you'll be asked to find now the centre of the circle and the radius. So let's consider all you're going to be shown in the exam is this little segment right here. Remember, a segment is just a part of a circle cut off by a chord. So we got 3, and we've also got 5 and 5. If that whole thing is 10, that's 5 and 5. So again, using the intersecting chord, what we can do is the following. Taking it now, and I'll draw it in this circle. If I extended this line down here, that is going to be now the diameter. That is all of the diameter, and this is what I've got here. So what I'm going to say then is that this is going to be 3, this is going to be 5, this is going to be 5, and this will be x. So we can see from here that my diameter is x plus 3. So the radius is going to be x plus 3 divided by 2. Now there is a formula for this, and it does get quite complicated. At this level you wouldn't be expected to use it. You would just be asked to find now the radius of a circle given. All you're going to see in the exam is this part right here. You're going to be given this, just this little segment right here, and you'll be told now that this is going to be 10 across, and then this part's going to be 3. So let's go ahead and look at this. So what we've got then is the following. We can say that 3x is going to be equal to 5 multiplied by 5, or 5 squared. So x will be equal to 25 over 3. So that gives me this length right here. So this is 25 over 3, and that's the length from here to here, but we can't see because we don't have it in the diagram. So all we've got to do is add these two together and divide by 2, because this is going to be the radius and this is going to be a radius. That's a radius, that's a radius. So I'm going to have now that the radius is going to be 3 plus 25 over 3, and we're just going to divide that by 2. So what's that give me? That gives me 34 over 6. So the radius is going to be, I'm just adding these fractions now, 34 over 6, hopefully 34 over 6, which is going to give me, what's that, 17 over 3, so 17 over 3 centimetres, and that's now the radius, so just under 6. So that's what we end up with. Hopefully my maths has held up on that, and you can see what I've done. But that's how you'd work out a scenario like that. So in some exams you're going to get this sort, in some exams you're going to get this sort. Now, depending on which one you do, you might not get this one, or you might not get this one. Different ones do different things, but certainly you're highly likely to get this type and then the one before. So the intersecting chord and then the secant secant. You don't have to prove them, you simply have to be able to work with them. So there we go, brief introduction to intersecting chord theorem and secant secant theorem, or secant theorem, and then finally the secant tangent theorem, and looking at a practical application. So with this last one right here, often these are given to be now part of a door, and this now is the window above. So when you see this segment above a door, so for example now let's make this into a door. Let's say now that you would be given a door, and it would be asked, you would ask how much glass you need from what radius circle to make the top part of this door. So if you're given a practical application, simply use that theorem. So there we go, that's the intersecting chord theorem and then similar theorem.